Integration as the reverse of differentiation. Integration by recognition, also called the reverse chain rule. Example 1. So I have some function raised to a power. So in this case 3x squared plus 8 raised to the power of 5. So to differentiate, the power comes to the front. The original function inside the brackets is here, reduce the power by 1. So this is the first part of the process here. So the 5 comes to the front, reduce the power by 1, and then we multiply by the derivative of the function inside the brackets. So differentiating 3x squared plus 8 and multiplying by it like this. That's the differentiation process done. Integration is in the reverse order. So we start on the right and we go to the left. So if we integrate all of this, we're back to 3x squared plus 8 to the power of 5 plus a constant of integration. Example 2, we're differentiating a natural log. So my f of x here is 1 plus 4x squared. So I need to take the f of x, put it into the denominator. So the 1 plus 4x squared goes into the denominator, and then we differentiate f of x, and that goes into the numerator, like this. That's the differentiation done. Integration is the reverse order of differentiation. So if I integrate 8x over 1 plus 4x squared, I get ln 1 plus 4x squared plus a constant of integration. Okay, so to integrate this function, I need to think of something that I can differentiate to get something similar to this. So if I start off with x squared plus 5 as a function raised to the power of 4, and then differentiate, and one of the results of the chain rule gives me this. This is where I have a function in brackets raised to a power. The power comes to the front here. Reduce the power there by 1. Differentiate the function inside the brackets, we get 2x, we multiply by it, simplify, we get this, and this looks similar to this, apart from that 8. So differentiation takes us from here to here. So if we integrate this, we get this, like so. So now we are allowed to multiply or divide both sides by a constant, not by any x term, but only by a constant. We can multiply or divide. So if I divide both sides by 8, so if I divide by 8 on this side and divide by 8 on this side, these cancel. So now I'm integrating exactly what I've got here. These are the same. So here's the answer, plus c. And the key thing in all of this is to figure this out. Example 4. To integrate this fraction, I have to think of something that I can differentiate to get a fraction. So if I differentiate a natural log, I'll get f dash over f, so the derivative is 2x, and this function goes into the numerator, and that doesn't look all that different to this. Yeah, they're very similar. I could multiply by a constant or divide by something and they would be the same. So if I differentiate this function, I get this. So if I integrate this function, I get ln x squared plus 4, and that's the order in which I need to write things. If I integrate the 2x over x squared plus 4, like so, I get this, the log function. Now this looks similar, but there's no 2 in the numerator. So I need to modify both sides. So if I multiply this by a half, so that half and that 2 will cancel, I have to multiply this side by a half. So now this fraction and this are identical. Here's the answer, plus c. Once again, this is the main part. How do you figure this out? and this comes with practice. Example 5. So what can I differentiate to get something similar to this? So if I start off with sine x to the power of 4 and then differentiate, and this using the chain rule where you have a function in brackets raised to a power, so I've got sine x and it's all raised to the power of 4, so I can think of it like this. And if I'm differentiating this, the power comes to the front, I've got my function inside the brackets, reduce the power by 1, and then I differentiate sine. If I differentiate sine, I get cos. I differentiate the angle and I get 1, and then simplifying gives me this. And this time no adjustment is required because this result is identical to this. So what we have is, if I differentiate sine x to the power of 4, I'll get 4 sine cubed x cos x. Now in reverse order, if I integrate 4 sine cubed x cos x, I will get sine x to the power of 4 plus a constant. Example 6. So what can we differentiate to get something similar to this? And all of the x terms need to be correct. The coefficient here can be different. We can deal with that by multiplying or dividing by a constant. But the x terms have to be correct. So I could try this, and that's a function of x raised to a power. So I would get, from differentiating, the same function inside the brackets, the power comes to the front, reduce the power by 1, and then I need to differentiate secant, which from the formula book for differentiation, differentiating secant gives secant tan. I have to differentiate the angle x, which gives 1, and then multiply by it. It's not doing anything in this case. And then simplifying, I've got a secant x term here. There's a secant x to the power of 4, so secant x to the power of 5, like so. And I've got the wrong power on my secant term, and there's nothing I can do by multiplying by constants between here and here that will change this. So this is wrong. Okay, so this time I'm trying secant x to the power of 4. So the power of 4 comes to the front, reduce the power by 1, same function inside the brackets, differentiate secant x, I get secant x tan x, differentiate the angle, I get 1, I multiply by 1. Simplifying, because there's a secant term here and a secant cube term here, and this time I have my tan term and I've got secant x to the power of 4, exactly what I'm looking for, and there's no adjustment required on the coefficient here either, which tells me that if I integrate all of this, my answer will be secant x to the power of 4 plus a constant of integration. For practice, try these questions.